Hello, Chem classes, and welcome to our next unit. If you're starting to watch this, you should have completed the exams beforehand and ready to move on to this next topic. So in this next unit, we are going to give you an overview of how to deal with quantities when planning a chemical reaction. The title of the chapter is a little bit misleading. It's just called Chemical Quantities. We kind of dealt with that when we learned about moles and molar mass. Now we're going to look at quantities in chemical reactions. So we've already learned about moles and molar masses, and you're going to need that information in order to do this chapter. And the goal of this chapter is to teach us how to use the balanced chemical equation in order to figure out how to predict the quantities of things that you need, if you know how much of one thing you have. So to remind you before we start what a balanced chemical equation tells us. So when we balance a chemical equation, we use these balancing numbers or coefficients to give us the relative number of molecules or the relative number of moles in a chemical reaction. And we do this by balancing the atoms that are on both sides, and you probably remember that from the chapter where we worked on that. This has nothing to do with mass. The reason that mass is conserved is because atoms are conserved, but those balancing numbers don't mean grams. They always mean some kind of counted quantity, like moles or molecules or atoms or whatever we want to use as that counted quantity. So it gives us the relative number of molecules or moles of reactants and products. So here's an example using this combustion reaction. Notice the oxygen and the products of CO2 and water. And in this case, the combustion is of the molecule ethanol, which is produced by yeast in fermentation. Fermentation is a process that happens when your bodies break down sugar. Yeast, when they break down sugar in the absence of oxygen, ferment sugar into alcohol. And then that alcohol can actually be consumed when oxygen's present, so your body can break it down further into carbon dioxide and water. This equation is balanced. The balance is one molecule of ethanol reacts with 3 molecules of oxygen and produces 2 molecules of carbon dioxide and 3 molecules of water. So if you notice all the comments on the slide, we can molecules, which is what they do in this part of the slide, number 3, or we can think of it in a different quantity of counting. So moles, remember, are a counted quantity. And we work with moles because we can't work with single molecules of things. There's no way to measure those out, but we could have a mole of ethanol. So if we change the word at the beginning, instead of saying 1 molecule of ethanol, we could say a mole of ethanol molecules, or just a mole of ethanol. Reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. We've just changed the quantity. We could say a dozen molecules of ethanol react with 3 dozen molecules of oxygen to produce 2 dozen molecules of carbon dioxide and 3 dozen molecules of water. Notice I'm never saying 1 gram of ethanol plus 3 grams of oxygen. That is not a counted quantity. We have to do things that are counted. So any count where we have the proportion of 1 ethanol, 3 oxygens, 2 carbon dioxides, and 3 waters, we can use any quantity of counting. And for the most part, in this chapter, we're going to use the mole. So let's try an example. Here is an unbalanced equation for the reaction between copper 1 sulfide, is Cu2S, and copper 1 oxide, Cu2O. This is an unbalanced equation. The products of this reaction are copper, solid, and SO2 gas. Now, this doesn't fit any of the patterns of substitution that we saw in our classifications. It doesn't matter. They're not asking us to classify it. So the first thing we need to do is to balance this equation. So let's start with our unbalanced reaction. And we can see in this unbalanced reaction that we have 4 atoms of copper, 1 atom of sulfur, and 1 atom of oxygen. And we have 1 atom of copper, 1 atom of sulfur, and 2 atoms of oxygen in the products. So since copper is all by itself over here, but it's in both of my reactants, I'm going to leave it to balance last, because anytime I change anything over on the reactant side, I will be changing copper as well. So I might as well leave copper till the end, because then I can fix everything with just one number. So I look at my other 2 elements. I see that sulfur right now, there's 1 in the reactants, 1 in the products. So I'm going to leave sulfur alone. So I'm going to put a 2 in front of this Cu2O, and I did it in red so that we can balance the oxygen. So I have 2 oxygens over here, 1 over here. So now I have 2 oxygens in the reactants. When I did that, it also changed the number of copper. So I still have 2 copper from the copper 1 sulfide, but now I have 4 copper from the copper 1 oxide, so I have a total of 6 atoms of copper. And my product stayed the same because I didn't change anything over there. So now if I look at my balancing, my sulfur atoms are equal, my oxygen atoms are equal. The only thing that needs to be balanced now is copper. If I just put a 6 in front of the copper, I now have a balanced chemical equation. So if we read through this, we could say 1 mole of copper 1 sulfide reacts with 2 moles of copper 1 oxide and produces 6 moles of copper and 1 mole of sulfur dioxide. And my balancing is complete. So after balancing the reaction, they want us to determine how many dozens of copper atoms can be produced from a dozen molecules of copper 1 sulfide and 2 dozen molecules of copper 1 oxide. So again, here is our balanced equation. So instead of just using 1 molecule, we're now thinking dozens of molecules or dozens of atoms, but the proportion stays the same. So if I start with 1 dozen copper 1 sulfide and 2 dozen copper 1 oxide, I should make 6 dozen copper atoms because the proportion is still the same. If I start with 1, I would need 2 and 6. If I start with 1 dozen, I need 2 dozen, and I make 6 dozen. The second part of the question asks us to do this in terms of moles. Again, it's just a counted quantity. So instead of 1 molecule of copper 1 sulfide, I'm going to need a mole of that. 2 moles of the copper 1 oxide, and that gives me 6 moles of copper atoms. So the answer should be, for the first one, 6 dozen, and for the second one, 6 moles, because the proportion stays the same, whether I'm talking about individual molecule, a dozen molecules, or a mole of molecules. As long as I keep the proportion the same, then the balance is upheld. So hopefully here the answer will be D, and indeed the answer is D. So on this slide, they're simply summarizing what we just worked through in the prior problem. And in this case, rather than giving us a balanced equation, they're also showing us pictures. So the balanced equation predicts the moles of products that you will produce if you know a given mole of one of the reactants. So in this example, our balanced equation is 2 moles of water, when it breaks down, produce 2 moles of hydrogen and 1 mole of oxygen. That's my proportion. If I double this and I have 4 moles of water, the proportion has to be upheld. So for every 2 waters, I make 2 hydrogens, so they're equal. For every 4 waters, then I would make 4 hydrogens. For every 2 waters, I make 1 oxygen, so for 4 waters, double this, I double that. So that's how this proportionality works. We are going to learn how to do it by doing conversions, because we don't always have simple things of doubling or changing to a dozen. Sometimes we have quantities like 2.75 moles of something, and we want to be able to still maintain that proportion. So on the next slide, we are going to talk about this new conversion factor. So one thing that might be helpful is if you think of a chemical reaction as kind of a recipe. If you were making a recipe, all the ingredients in a recipe are in proportion. So I'm just making this up, but say you were making a cake and the recipe called for 4 cups of flour and 1 cup of sugar and 2 eggs. If you wanted to double the recipe, make 2 cakes, You would double the flour, 4 goes to 8. You would also double the sugar, 1 times 2 is 2, and you would double the eggs, so you get 4. The proportion is still the same. For every 4 cups of flour, you need 1 cup of sugar and 2 eggs. This is sort of the same thing. It's just that once you start using chemical words, it seems harder. So our new conversion factor that we are going to define in this chapter is called the mole ratio. And the mole ratio is actually very simple. This is our last new math for the semester. This is the last time we are going to be introducing a new conversion. The last unit will have no conversions in it. This conversion factor comes from the balanced chemical equation. So it's sort of like molar mass. Every time you use a mole ratio, it's defined by the equation you're working on. Just like every time you use a molar mass, it's defined by the substance you're working on. And the mole ratio will allow us to interconvert the moles of one substance in an equation to the moles of a second substance. And this can be done no matter which substance you know. So say you're doing a reaction and you want to make a certain number of moles of something. You can use it to figure out how many moles of reactant you need to start with in order for you to get enough product. So as long as you know one of the components of the reaction, you can calculate the amounts of all the other components. And the only thing you need to figure this out is your balanced equation. So far we've been working with easy things like doubling or going from 1 to a dozen. Usually we don't have such even numbers, but the proportions still have to hold, and that's what the mole ratio will allow you to. So now let's take a look at some conversions. Like all conversions before this one, we are going to ask ourselves 3 fundamental questions. What do we know? Where are we going? And how can we get there? In this case, we need to start with a balanced chemical equation. And the one that they have here, they have given it to us balanced, so we don't need to take time to balance it. So this is sodium hexasilicate, which we're not going to worry about, plus 4 sodium yields silicon plus 6 sodium fluoride. And then the question is, how many moles of sodium fluoride will be produced if 3.5 moles or 3.50 moles of sodium is reacted with excess Na2SiF6? When they use the word excess, they're just telling you you have enough of the second one, so you don't need to worry about running out. So don't really worry about that. The thing we need to worry about is the thing we know, which is the 3.5 moles. So again, let's define. What do we know? We know the balanced equation. That is essential. And we're starting with 3.5 moles of sodium, 3.50 moles of sodium. That is the only quantity that is presented in the question. So it's the only value that you have to work from. There's no other numbers given, so there's nothing else you could even start with. Where are we going? The question says, how many moles of NaF will be produced? So that's where we're going. And question number 3 is, how can we get there? How can we get there? Is the mole ratio. The mole ratio that we're going to use is the mole ratio between the 2 things that we have in the equation, what we know and where we're going. So the mole ratio is going to be the moles of what we know, which is sodium fluoride, and the moles of where we're going, which is sodium. Okay. Just like any conversion, we set this up so that what we're going to is on the top of our fraction. So here's what we know. We know the moles of Na, 3.50. Here's where we're going. We know that we want to find the moles of NaF. Here's my mole ratio. The unit is moles NaF. That goes in the numerator. I'm converting from moles of Na. That goes in the denominator. The numbers come from. The number in front of sodium is 4. The number in front of NaF is 6. Those are the numbers that go into your mole ratio. The mole ratio is defined by the balancing numbers in the chemical equation. 5.25 moles per 3.50 moles is the same proportion as 6 to 4. They're the same relative amount. It's just that we didn't start with 4. We only started with 3.5, so we can't make 6. We're going to make a little less than 6. So let's try another example. So here we are going to look at a combustion reaction where the molecule propane, C3H8, is burned in the presence of plenty of oxygen. So again, more oxygen than we need. And we are starting with 3.74 moles of propane. It's burned in excess oxygen, and we want to predict the number of moles of carbon dioxide that will be formed in this reaction. So again, we start with our balanced chemical equation, and then the first question is, what do we know? We know moles of propane. Where are we going? The problem is asking us to find the moles of carbon dioxide that are formed. How can we get there? We get there by using the mole ratio. In this case, the mole ratio has what we know on the bottom, what we're trying to find on the top. So we know moles of propane. That goes on the bottom. The number in front of propane is 1, so that's the number. We're trying to find moles of carbon dioxide. That goes on the top. The balancing number in front of carbon dioxide is a 3, so that goes on the top. When we set up the math, we now have 3.74 moles. We multiply this by our mole ratio, and we can see that the moles of propane now are going to divide out. So it's 3.74 times 3 divided by 1, and the unit that is left is moles of carbon dioxide. So when we do this on the calculator, let's see what we get. We have 3.74 times 3, and with significant figures, it should be 11.2. So that is one of the, so let's see if 11.2 is the correct answer, and that is the correct answer. When you feel ready, try a few problems on the worksheets before you move on to the next presentation, where we're going to bring in starting with mass, because we can't weigh moles. And that's always what we end up doing, is bringing in starting with mass. So that is the end of the first part of this unit.